Hey guys, welcome back. We're now in Unit 13 post spring break, and we're going to talk about intermolecular forces and physical properties. So, before spring break, you were introduced with the polarity lab to different uh, relationships between physical properties and attraction between molecules. So, molecules are particles with a complete octet. So this would include everything from water to methane gas to sodium chloride to sugar to hexane. So we had a variety of different molecules that we investigated in the polarity lab stations. All of those have complete octets. And so when we talk about intermolecular force, we're talking about the force of attraction between molecules. And that force of attraction between molecules has everything to do with physical properties like melting and boiling point, rates of evaporation, solubility of both solids and liquids. So all of those properties we explored in the polarity station lab relate back to the idea of attraction, which is not a new term. We're just revisiting attraction again. And so when we talk about intermolecular force or attraction between molecules, we can rank intermolecular forces based on strength of the bond. So when we look at this hierarchy, we have strong bonds, and we have weak bonds between molecules. And so the strongest, which is no surprise, are the ion-ion bonds. So in Unit 9, when we studied ionic compounds, we learned that the strength of attraction between ions is dependent on both charge difference and also ionic radius. And so when we look at aluminum oxide, for example, aluminum and oxygen are both small in their radii, and they're also large in their charge. So aluminum's a +3, oxygen's a -2. So the force of attraction is really high, which makes the strongest bond. And so as a result, in room temperature conditions, salts like aluminum oxide will be solid. Greater attraction, less spacing. Less spacing obviously means solid state. Cesium iodide, also ionic, but here we have a +1, -1 charge difference and larger ionic radii. So not as strong as aluminum oxide, but still within that ion-ion distinction. The next ranking would be hydrogen bonds. And hydrogen bonds form between atoms that have larger electronegativity difference and therefore greater attraction. So hydrogen and oxygen, like in water, or hydrogen and fluorine, hydrogen and iodine, all of those would be example of stronger hydrogen bonds between molecules. And then next, we talked about dipoles and the fact that with polar covalent molecules, you have the partially charged ends, partial positive, partial negative, because of the fact that some atoms have a greater electron affinity than others. And so they're not full charges, there's just a greater pull on one end of the molecule because of a more electronegative atom in that molecule. So that would be your dipole-dipole intermolecular force. And then lastly, London dispersion are the weakest intermolecular forces, and these form within nonpolar covalent molecules where there's an equal distribution or affinity for electrons. Okay. So like I said, the fact that these molecules have differences in attraction affects their physical properties. So when we talk about ion-ion forces, we have ions, positive and negative, that attract to form a crystal lattice. The attraction is strong because we're talking about full charges, like in sodium chloride here. We're talking about a +1 sodium ion attracting a -1 chlorine ion to form a crystal lattice. that in the real world looks like this, right? So because of greater attraction, these are solids at room temperature. And the attraction between molecules within that crystal lattice has everything to do with, like I said, both ionic radius and charge difference. So not all ionic compounds and crystal lattices are created equal. And we saw that in the lab station where we compared solubility of barium chloride and calcium oxide. So dipole-dipole forces would be the force of attraction between polar compounds. And in a polar compound, there may be a more electronegative end of the molecule. And that means that that atom is pulling with greater force on the electrons, making that end of the molecule partially negative, whereas the opposite end would be partially positive, less electronegativity. And so those partial charges on either end of the molecule create a kind of stronger force of attraction between them. And we can see that here with these polar molecules. So the partial positive end attracts the partial negative end of the next molecule. So that would be ethanol and then chloroform there. And here we go. Another example of dipole-dipole. Actually, this last one I think was methyl alcohol, not ethanol. So the partial negative end of the methyl alcohol would be the end with the oxygen right here. And the partial positive end would be the end with the hydrogens. And then here, the end with the hydrogen is the partial positive on the chloroform. And the ends with the with the chlorine would be the partial negative. So these two attract. Makes sense, right? Hydrogen bonds are an example of a special kind of dipole. It's a stronger attraction than other dipole-dipole forces. And this forms when hydrogen is bonded to a very electronegative atom like fluorine, which is the most electronegative, or oxygen. So like these compounds are crazy attracted to each other, right? It's about 10 times the strength of any other dipole-dipole interaction. And we can see that with water especially. So I'm going to create a little water video that you guys can see some of the physical properties of water, and we'll relate that back to the strength of this hydrogen bond. Another example of hydrogen bonding would be in DNA. And you guys probably explored this in biology. I know it's been a while. But the bonds that hold the rungs of your ladder together are hydrogen bonds. And so this attributes to some of your physical properties, right? So this is your the backbone of DNA. And those base pairs are bonded together because of those strong hydrogen bonds. So that's kind of cool to think about. What makes you unique has everything to do with the strength of those bonds. So then we can talk about something called London dispersion forces, which is a fancy way of saying the attraction between nonpolar molecules. And here the intermolecular force is very weak because, as you know, with nonpolar molecules, there are similarities in electronegativity, and the dipoles generally cancel. So examples of that would be here octane and hexane. But when we compare these two molecules, if you look at octane, you can see that octane has 8 carbon and 18 hydrogen, which makes for a lot more electrons. So more atoms, more electrons. More electrons, greater likelihood that you're going to have electrons kind of sharing similar spaces, even though they repel, which will create something called an induced dipole. And so that induced dipole, it's instantaneous, it doesn't last long, but it increases attraction between molecules. So when we compare octane to hexane, the attraction between molecules of octane is greater than those of hexane. And this obviously affects the physical properties. And we saw this with the lab station where we compared methane, CH4, to hexane, C6H14. Okay, last but not least, the weakest of all forces are called dispersion forces. And this is when you have two atoms that are near one another that create an induced dipole in the sense that there's a weak attraction. Electrons are trying to kind of repel each other, and therefore one end of the molecule is going to have a dipole just instantaneously. It won't last forever. It makes for a weaker force of attraction between those molecules. So examples of types of molecules that have dispersion forces would be like the noble gases, for example. All right, I'm going to stop here for now because of the fact that I want to give you a few examples in my next little segment to show you differences between types of molecules and physical properties. So signing off for now.